Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Last week, I believe we got to the point where we have sort of a pretty clean version of our rendering system working, where we really eliminated a lot of sort of the weirdnesses that we had inherited over the work on our renderer, where we, kind of had a bunch of stuff we were doing to support, 2D sorting and all these other sorts of things. We went to the 3D pipeline, a lot of that stuff wasn't necessary anymore, and so we kind of cleaned everything out. And we now have stuff working in what is a pretty sane fashion. You can actually see that now we've just really only got one basic operation that we ask our renderer to do, and that is to draw a series of textured quads, which is what you would expect in a sprite-style game. And to that end, we've been able to implement some additional features, like we have now depth-based fog. And so this weekend, probably, I think the best thing to do would be to just look at some of the rest of the cleanup that might be implied by this transition, and to look at other things that we may need to do along those lines. So, for example, one of the things that we had working at one point in the original renderer was the ability to alpha fade out the sort of part of the, I'm not sure how to describe it really, but in the case where the game had a stack of levels on top of each other, a stack of rooms on top of each other, so you'd imagine stairwells going up and down in between these rooms or something like this, and the player being able to navigate through them. In that case, you ended up in a situation where you could have a room, completely obscuring the view of the player, and obviously this is not good. So one of the things we implemented in the older version of the render was the ability to alpha fade out that top level room. And the problem that we face now is we don't have that anymore. And in order to implement that again, the way that we implemented it originally would require adding in a lot of these sort of elements that I don't think are very useful, such as sorting sprites or introducing some kind of a partition where the people who are specifying the sprites artificially tell you when you've hit the set of sprites that's going to be in that top part versus in the part that shouldn't be alpha faded out and stuff like this. And so what we're kind of interested here is looking a little bit more closely at how we would alpha fade something out more automatically, right? Like, what can we do in this case to prevent things from obscuring the player in a more automated way, right? That's what we're really looking for. So what I'd like to do today is start to investigate that a little bit more. And I think we've kind of got two things on the table that we're going to need to sort of work on with respect to that. The first thing that we're going to have to work on is just how we will approach such an alpha fade. The second thing that we have to work on is our camera. We kind of need to upgrade that to 3D now. Obviously, our renderer supports a full 3D camera. Our game at the moment doesn't really have a very solid understanding of what the camera is or where it's looking. It's kind of ad hoc and always has been, so now would probably be the time to upgrade that to something a little more intelligent, a little more sensible. And so we've got to deal with those two, and then eventually after that is done, we probably have some other sort of remaining issues to deal with, such as finishing up our clip-rect support, because right now our debug UI, although it is re-enabled, we didn't fully port some of that stuff. Like the clip-rect stuff is not properly working in there, if I remember correctly. We've got to deal with our particle systems, right? Right now, they are not able to output efficiently, really. Our renderer now has the ability to intelligently do things, such as not switch textures every particle if we wanted it to. So we could batch up our particles into large groups and submit them much more efficiently, which seems like a pretty good idea, because particles probably at the end of the day are going to comprise a lot of our draw calls if we were actually changing textures every particle, right? That's a very expensive thing to do. And it's not at all necessary now that the Z buffer is sorting things, so our particle systems probably want to come down in a very specific additional way that would add one more set to the renderers, or it could even use the same thing that we've got now, but just a Boolean that says whether the texture changes every quad or not would be sufficient for us to make sure that that wasn't going to happen. So we've got a lot of stuff we can look at now, and I don't have any real opinion about anything needing to happen first. We're just trying to sort of sweep through and make sure our new renderer is working nicely and everything is good. So I'm just going to jump in there and start doing stuff. If you would like to jump in with me, it's 376 today. So use day 375 source code as your starting point, and that is what I am going to be working with as we go. So here we go in terms of just checking out where we are at the moment. If I open up the code as it stands, let's go ahead and run that. This is what we're looking like right now. And everything is pretty good here. There's nothing particularly problematic as we go. You can kind of see that actually you get a pretty nice 3D effect here. Again, at some point we're probably going to have to, you'll notice we're not getting our 60 frames a second. That's because, again, of that function that we have in there that does the get traversal stuff is kind of bad. So what I could do is I can just compile with optimizations on to fix that for the time being while we're playing around with it. But it would be nice to run at 60 frames a second in debug mode, and really there's only a few small reasons why that's not possible at the moment. Okay, so anyway, here we are at 60 frames a second. And so if I kind of come down here, you can see you know, some of the problems that we do have. So here I am, you know, bouncing around at the bottom level, and you can kind of see that you'll have to ignore the fact that currently we allow familiars to float in between levels, which is not particularly good. So that dude right there is literally just kind of floating up in the air, which he's not really supposed to do. But, you know, what are you going to do? Anyway, you can see that when I get down here, it's very problematic because, you know, obviously we would like the upper area to kind of go away at this point, or something to happen here. And again, there's just a whole host of problems here. We also don't really prevent you from hopping up in through the ceiling. Like you can see this happening a couple times here, right? We allow you to pick stuff that's not even really connected. If there's something blocking your ability to jump, we don't really prevent it. So, you know, if you're coming along here and, you know, this guy's in your way or something, well, or I guess that guy's in my way, when I hop, I'm allowed to kind of hop up, I believe, here. I'm not actually 100% sure if that's true. Well, it looks like it skips over it there, so I'm not sure why it did it there. But point being, our hopping stuff is completely, you know, just placeholder at this point. So we get some weird stuff like that. But in terms of the renderer, that's really not an issue. What is an issue in terms of the renderer is what we're looking at right now, which is a situation that will absolutely occur even if the hopping code is all quite correct. And that is specifically that when I'm hopping along down here, if the camera was, and again, the camera is just kind of picking randomly at the moment, but if the camera does decide to be up here, which is a reasonable place potentially for it to be, we would like this to go away. And more specifically, you know, as you come up and down those stairs, as the camera moves in and out, we would like it to go away in a nice, clean fashion, right? So I think the first thing that I want to do probably is fix the camera code. And so there's a couple of different things that have to happen there. But basically what I'd like to do is make it so that the camera is doing really, you know, more what we expect it to do in the final game, right? So, you know, actually have the camera code properly follow the person around, properly understand what room it's looking at, and properly understand when it would need to transition between two rooms in order to better support the player's view of things, right? And we don't really have that right now, largely because when we move to the 3D system, we haven't really finished upgrading our notion of rooms in order to really like allow the camera to think about them properly. Okay. So let's see what we can do with that, and you know, with an eye towards actually having the camera be proper now. I'm going to go ahead and eliminate some of the rooms that we have, just so we can keep things a little more straightforward for debugging. I want to get us down to a simpler case. Rather than 2 rooms, you know, let's just try, I'm sorry, rather than 10 rooms, Let's try 2 or 3 rooms here, which again will also speed things up because again it's that one function that costs all our time, so we'll at least be a little bit faster too. So what we're going to look at here is just this one case. You can kind of see what we're looking at here in terms of, you know what else I should probably do? Turn off fog when we're in debug mode. So fog should probably only be on here, and when we're out here we should probably turn off that fog. It's pleasant though, isn't it? I like it. It's just not really conducive to debugging. That's relatively straightforward to do, thankfully, because the way that we structured the fog is that when you actually do a setup push, right, when you come in here to the camera setting code, which is here, we actually know which one we're doing, right? We know whether this is a debug camera or not, because you can see that we set the flags here. So what we could do is say that in this case, the fog start distance, end distance, and direction there, we could go ahead and say, let's only do that in the case where we're actually not debug, you know? And so in the case where we're not debug, I'd have to see here, it always uses the last setup. So we probably want to do here, again, is make sure that the fog direction is getting cleared. So I think what we want to do is say, in fact, really, I guess we don't really need to worry about setting the start and end distance. Really, all we need to do is worry about that fog distance. Because remember, this fog distance is what is the vector that will be used as a dot product to determine how far away something is from the camera. And again, we've set it to the camera's location because we set camera P, right? We set camera P right here, and we're going to measure along this vector that camera P, right? But the crucial thing to understand there is that when we do that measurement, at that point, we can just say, well, okay, if it's a debug camera, just measure along something that never will produce any value at all, right? If we give it the 0 vector and say measure how far away something is along this, it'll say, well, it's 0 along it, because the dot product with it is always, again, AB cosine theta. Remember, I say that every time. That AB cosine theta, in this case, if the A or the B were 0 length, then the whole term is 0 length. In this case, we're just giving it a direction with 0 length, which means that when you specify a debug camera, you will get no fog at all. And you can see that now when I switch between them, right? There's the fogging. You can see that it gets darker as it goes back and closer to the gray value. When I switch to the debug camera, now they're all the same color, which is exactly what I want. And so now if I want to look at things like so, I can look at them without them fading away, which is what I wanted. And so there's my 3 rooms stacked on top of each other that I'm going to use here. And what I'd like to do first, again, is kind of return us to a sort of a more rigorous way of defining what a room actually is. And I'm going to have to think about that a little bit because in order to really figure out what's going on with that, I'm going to have to start thinking a little harder about how we're defining some of the things that we're defining. For example, I think our collision volume stuff is kind of a little crappy. It's not very good right now. And the way that we're sort of doing that is probably not the best way. For defining something like a room, we kind of just want to say, here's what the bounds of the room are. And I don't know that we really want to go into all that much more detail than that, to be completely honest. So I feel like there's a certain degree of bogusness to how we're doing that, and I'll have to double check and make sure I don't want to change a little bit of that as well. But what I'd like to do now is basically have something that creates sort of boundary, right? A bounding box here where I'm going to draw a volume that shows where each of these rooms considers itself to be. And one of the problems with doing this, and I don't really know what our definition of it should be, but one of the problems with doing this is I don't really know how to define the extents of these rooms all that well. But what I think should probably be the case, and again, I'm just sort of speculating here from looking at this, is what I think should probably be the case is that a room should be defined as being the lowest point that any of these sort of standing pieces, probably the lowest point of one of those up to where the next room would have started. So like the lowest point on one of its to the lowest point on its upper neighbor, that's the size of a room, right? Stated alternately, if each room was going to be roughly the same size stacking-wise, which, again, we don't actually require them to be for any particular reason, and so we don't have to do that necessarily. We can have some rooms that are taller than other rooms. In order to make that a little cleaner, I just have to figure out some way of saying, okay, let's just make sure that when we define what a room is, when we place the standing blocks on it, let's just never put any of those down low enough that they, cross through the bottom of the room's lower plane, right? That's just one intuitive idea about how those should be specified. I don't have any real reason for picking that. Just a purely, it's a pure conjecture on my part. I don't have a lot of, I don't have anything to back that up. So I don't know if that'll actually be what we do, but something like this needs to happen. And so what I'd like to do now is get to a place where we can see that happening. Maybe add the ability to draw that. I don't know what that's doing there. All right. Maybe add the ability to draw that in so that I can see it, because I would like to be able to verify that as something that's going on. So I would like to be able to see those boundaries. And at the moment, the only thing that we have right now in terms of what we can draw are these sort of flat rectangular outlines. And so I think what might be more interesting to do at this point is say, let's add something that can draw a volume. I want to say that Miblo actually requested this last weekend, and I believe at that time I said that would be a very good idea. Not only do I think it's a very good idea, but I think we should go ahead and do it right now, because I'm going to need exactly that. So let's take a look at how that would work. So you can see on here we've got a notion of a push rect, and we've got a notion of a push rect outline. And the interesting thing about the push rect and the push rect outline is at the moment they all assume that they're going to draw a rectangle which is flat to the world Z, right? In other words, if you were to take the flat sheets of the game, like a flat sheet, wherever you wanted to imagine it, and you imagine us sitting here at the top looking down on this here with our little camera. You know what? I'm going to draw an eyeball because I'm more used to drawing that. Boop, boop, boop. So if we're looking down on this with our eyeball, previously all we could really do is say, let's draw, a thing that looks like this. And the way that we were drawing that is either we'd solid fill it, that was push rect, or push rect outline would just draw several solid filled ones that just expanded along sort of the X and Y axes to produce 4 filled rectangles, which made it look like an outline. So the question I have here is, can we just go ahead and say, let's get something that's like push volume outline that basically does exactly the same thing. So if I want to here, I'm going to try it. I like that expanded to inefficient. Inline, there are definitely a lot of things we do that are inefficient here. Maybe someday we'll fix those, I don't know. So if we have a push volume outline, and I take, basically the same parameters here. So I've kind of got an object transform, and then instead here, I guess I would take a rectangle 3, assuming we have one of those. I don't remember if we ever defined one of those. So there'd be no Z, there would just be a color and a thickness, and that would be it, right? And so this would be what we would be looking at. Okay. So if that was what we were going to do, and also these object transforms are probably things we could possibly get rid of by now as well. I should just mention that, because we're sort of, since we're fully 3D now, I don't know that the object transform is really all that necessary. If you take a look at what's actually in there, it's got almost nothing in it. It's really kind of irrelevant, and so this may be this may have become irrelevant. So at some point, we're going to probably want to do one final pass over this stuff where we're just like, okay, we're done with everything now. Let's just do a cleanup pass on anything that we think is kind of dumb. Because at some point we probably, after you do all your experimentation and work and you're like, this is what we're going with, you typically need a little bit of time to sort of straighten out the legacy vestigial remains. So if we push a volume outline here, then what we can look at and say, well, okay, we've got this ability to push these rectangles on here, but these rectangles are not really exactly what I want. Because if you look at how they work, again, they're very heavily biased towards having the z values be a specific thing. And that's not really what I want. So what I'd rather do here is I'd rather start looking more, for example, like at push cube, and say let's start with the push cube code, because push cube is really more what I'm looking for, right? In fact, let me kind of move this up here to where the push cube stuff is, and we'll take a little bit more of a closer look there. So I'm going to go through here and say, all right, let's go ahead and grab this this quaz group here, and I'm going to go ahead and put that into push volume outline. And you can see that we've got a bunch of stuff here like texture coordinates and stuff which won't really be necessary because we won't really be using a texture here, but that is kind of neither here nor there. What we will be doing in this case we'll be following push rect's example in one case, which is that we will not actually be setting any particular bitmap color, any particular bitmap value. We'll be using the white bitmap so that we don't get any contribution at all from it. So we're just gonna go ahead and do it that way. So what we'd like to do here is we'd like again to pass a rectangle 3 down. I don't know if we have one of those. I hope we do. Think we do. Yeah, we do. So what we want to do is take this rectangle 3 and we want to be able to draw something that looks to the viewer, again, only for debug purposes, so it doesn't have to be perfect, but that looks to the viewer like a outline of a volume, so you can kind of see where the volume is, right? And so if you look at what we're going to have to do, this set of push quads is not particularly useful to us, and the reason for that is this set of push quads is drawing faces, right? And so there's 6 of them because it's drawing 6 faces of a cube. But what we would rather do, right, is we want to draw the edges of the cube, right? So instead of drawing 6, there are 6 faces to a cube, 8 vertices. But if you look at how many edges there are, right, there's 1, 2, 3, 4 on this face, 1, 2, 3, 4 on the back face, and then 4 attached, connecting each one together. So there's actually 3 times 4, or 12 edges, right? We've got 8 vertices, 6 faces, 12 edges, right? So what we want to do is we want to draw these 12 edges, and we want to enumerate what all those 12 edges are. And so what we could do here again is sort of figure out a way to push some kind of a line segment that you can see. And so instead of a push quad, what I want here is push line segment or something like that, where I pass the group and the bitmap, and then I pass 2 endpoints and probably 2 pieces of texture data or something like this. Or maybe the texture is inferred because it goes along the line. And in fact, that's probably what would happen, right? And so what I want to do here is have the ability to specify for each of our points on the cube what's going on. So if you take a look, we've got negative x, positive x, negative y, negative z, positive z, and then we built these up, p0, p1, p2, p3, p4, p5, p6, p7, as the combinations of those things, right? And so what happens is, in this case, we're getting them from a different place, but other than that, everything can stay the same. So if you look at this, we can just say, like, okay, all of these values we can still extract out of our rectangle 3. So here's our rectangle. For example, this is just going to be min.x. This is going to be max x, right, because the positive x. And then these are all going to be basically equivalent. This is the y version. This is the z version, min-max, right? So then these p numberings are all totally reasonable and can be the same thing. And in this case, we don't really have, in terms of top color and bottom color, we really only have one color. We could make the color vary across the line, but at the moment, we don't really need to. So all I really need to do is specify one, oops. I don't know what that did there. We only need one of those, and I don't need to vary that at all. So all of this stuff can kind of be ignored. The same is true for the texture coordinates at the moment, although I guess what I could do here is, well, you know what, I'm gonna ignore it. So anyway, so when we want to draw the lines now, what I want to do is I want to draw line segments between each of these that's relevant. And so what we kind of need here is just a reason why, or how to know like which to do, right? How to know what we want to draw. We've got P0, P1, P2, P3. How do we know which ones to draw between? Well, what you can see here is essentially there. I know this is going to sound a little bit weird, but just bear with me. If you take a look at how the edges of a cube are formed, what you can say about it is an edge, a cube has an edge between any two vertices who differ solely by the positive or negative version of one of the variables, right? Like we were talking about before, this being center and dimension, or maybe we're talking about min and max. And so we basically have, you know, to define where all these are, we're always like, oh, okay, the vertices of a cube, right? Wow, that was good. The vertices of a cube are defined by the enumeration of all possible combinations of the min and the max for each coordinate, right? So if I have x, y, and z, I end up with min, you know, min, you know, min, max, min, max, min, blah, 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 right? And there's 8 of these because there's specifically 2 possibilities for each of these, min and max, and I'm doing all of them. So it's 2 times 2 times 2, or 2 to the third, which is 8, right? So vertices is basically the like 2 to the third. It's all the possible combinations of min and max, right? That's what vertices are, and that's why there's 8 of them. Edges, on the other hand, which is what I care about now, is slightly different. There is an edge between any pair of vertices where only one of these differs, right? So if I'm from this particular edge, and I've got, you know, let's say this is min, 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 if I want to go to another corresponding value, I have to go to max, min, 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 max, min, or min, min, max. Those are the 3 I could go to, right? And so if you think about what that means, is it means for each 8, you know, for each of the 8 vertices, there are 3 different ones I can go to, which would appear to be equal to 24, which is not what I said, right? I said there's 12. Why? And that is because the edge that goes in one direction doesn't need to be drawn in the reverse direction. So this edge, which went this way, doesn't need to be drawn in that way, right? Because I've already drawn it. So I only have to consider half of those, right? And that's where my 12 comes from. So if I want to draw these, all I have to do is start with each of these and do exactly that process that I just said, which is go to the ones that are one different from it. So let's just start at P0, for example. And I know that P0 is NNP. So PNP would be one of them, right? PPP would not be one of them because that switches 2 of them. NPP would be one of them. And now I know there's 3 that should come out of P0, so what's the other one, right? NNN would be the other one. And then the rest of these won't be, right? Like that one switches 2, that one switches 3, and that one switches 2. Right? So there's 3 of my edges, the ones that come off P0, right? Now to maximize things here, I know that if I picked P0 this time, right, what I should probably do is make sure I pick one that hasn't been talked about at all. So P2 has not been talked about here, so let's go to P2. So here's P2, that's positive, positive, positive. So negative, positive, positive, that works. Oops. Negative, negative, negative does not work. Positive, negative doesn't work. Positive, positive, negative does, that's P6. And similarly, positive, negative, positive works, because that's only one switch. So 1, 3, and 6, all valid there. right? And again, I never talked about P2 here, so there's no risk of duplication. All right, so one more time. You notice we have P0, 1, 2, 3, 4. We've never talked about 5. So let's go ahead and talk about 5. Here's P5. Positive, negative, negative, right? Never one that we've drawn to. So here we've got positive, positive, negative. That counts, so that's P6. Negative, positive, negative. That counts, that's P7. And now we've got... Let's see here. Positive, negative, negative. There we go. Positive, negative, positive. That's P1. Right? So now I've got all these guys drawn. P0 to P1, P0 to P3, P0 to P4, P2 to P1, P2 to P3, P2 to P6, P5 to P6, P5 to P7, P5 to P1, right? So I've got all those guys drawn. And again, don't have to worry about any duplication there because they're, we basically picked people who didn't have any overlap in common. Essentially, if you imagine, let's see if we can draw this out here. In fact, why don't I go ahead and do it so you can see what we ended up drawing. All right. So if you take a look at how this worked, right? We can look at what these were set up to be, P0, P1, P2, P3, right? So I'm going to draw the little axes here. I'm going to assume that we've got this. So here's Z, here's X, here's Y. So like this in the corner, for example, actually I guess it'd be this in this corner. This guy is, negative, 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 right? That's like negative in all directions. And then if we picked this guy here, this would be positive, 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 right? So anyway, if we take a look at where these guys are, P0 is negative, negative, positive Z. So we're on the positive Z. In fact, if you look at this, this is all the positive Z faces. It starts at negative, negative, so it starts at down here, right? This is P0. And then we go to positive, negative, positive, right? So that's going to right here for P1. Again, because it's that negative is it's not going up in Y. So this is P3, this is P4. And then, oops, P2, P3. Trying to make that a little clearer there. P2, P3, there we go. And then similarly, we've got the negatives here. We had negative, negative, positive, right? So we were doing exactly the same process. So this down here is P4, right? And it went P5. Oh, wait. No, we probably went the other way around, right? So P4 is negative, negative, negative. This is P5 is positive, negative, negative. So it goes down X. Now I guess that is what we did. P5. So P6, P7. So presumably, in that case, negative, positive, positive is P6. Yeah, positive, positive, negative. All right, well, I guess that's what we did. So anyway, those were our points. And if you look at what we're doing for line segment here, it's P0 went to 1, 3, and 4. So P0 went to 1, right, 3, and 4, which is exactly what we'd expect. We then move to P2, which is this saucy gentleman right here. And it was P1, P3, and P6. So that's P1, P3, and P6. And then we then move to P5, which is 6, 7, and 1, right? So there's 1. There's 6. Wait, how did we get 7? That's just... Did I mess that up? I've drawn something wrong here, because that would go like that, according to this diagram. 7 is negative, positive, negative. Right, which is there, that's correct. P5 is positive, negative, negative, which is this. So these two should not, yeah, that's a double switch. That's just wrong. That should have gone to 4. Always use a diagram, folks. There we go. And that would leave us with P7, which is what should have happened there, but of course I misread my own chart. I misread my own code here. Anyway, P7 in this case needs to go to anyone with one change away from it. So here's P7, negative, positive, negative. So positive, positive, negative would be one switch, so that's P6. What else we got here? That's 2. Here's 1, so P4. And finally, we would probably expect, negative, positive, positive? Yeah, P3. So 6, 4, and 3. There's 3, there's 4, and there's 6. And those are all the sides of our cube. So now that we've got all that underway, let me just sort these by ascending order here, because why not? 1, 4, 6, 3, 4, 6. So those are all of our line segments we would need to draw to form a complete volume. And so if I wanted to complete this here, all I need to do is figure out how to actually draw a line segment given the information that we're passed here. So I'm going to need that line color, right? And let's see here. Where's my push quad? Here's my push quad. So actually, I suppose this push line segment should probably come up here. Let's see here. Push quad. Here we go. And it's got that packing going on there. I'm going to do the same thing down here. So here's push line segment. It wants exactly the same stuff, right? So we're going to do game commands, render texture quads equals current quads. We're going to add a quad per line segment. We're going to add a bitmap to it, which is whichever this bitmap is that we're getting past. We're going to add 4 vertices, which is correct. But the way that we're going to add these vertices is now going to be different, right? So really what I could do, because I'm going to, because we're going to essentially use exactly the same code, what I could do is just push a quad here and just compute the values that I would push to the quad, right? So what I can do here is say, all right, we're going to go from this P to this P using this color. And I guess in order to be a little more consistent here, probably should do this, right? That's a little bit better. Similarly, I don't know if we want to specify UV coordinates. It's a good question. I'm not really sure. But at any rate, we're going to have to specify a thickness as well. So looking at this, what we need to do now is compute how to call this with what we're given. So here's the values that we're actually going to need, right? We have the group in the bitmap, so those are obvious. So now the question is just how do we compute the rest of these values? And so what we could say is, go ahead and move these out a little bit here. There we go. So this is what we want to figure out. And I'm going to have to name these slightly differently because since we already kind of have a nomenclature for these in the quad, I'd rather sort of have, this be, maybe this is from and from C or from P to P, like so. Just so you kind of say like, okay, I'm going from this point to this point, kind of an idea, right? So that's what we're looking at here. Now, we've got a bunch of work to do, obviously, to try and figure out how we would make these values given what we have. Some of them are easier than others. So for example, in the UV case, I think we don't probably want to support a lot of UV stuff here because we're probably never going to be really doing anything with these. So what we could say is, well, it's just going to be, you know, the basics UV. It's just going to map the entire texture to the line. Whatever, right? And maybe that's a dumb idea, but until we actually would have some reason why we might think of doing something else here, I guess I should probably do it this way. Until I think of some reason why we're going to actually use texture mapping with lines, I don't really think there's any need to get fancier here, right? Similarly with our colors, I think we can just always use one. In this case, we can just do one single pack down. Oh, well, I guess what we said is we could do a from C and a to C. So I guess in this case, I'm going to do a pack. So let's do it this way. Maybe I'll call that F. It's a floating point version. So we'll pack those two down, and then we know that like anything that's going to be on the from side, which I guess is these two here, we'll get that color, and anything that's on the to side, we'll get the other color. All right. So our main goal here is just to figure out what these points should actually be. And so let's take a look at a diagram so we can figure out what we're trying to do. What we've been given, in this case, is a situation that looks like this. And what we want to do is we want to draw a line segment, something that will allow us to get, you know, some thickness here, right? So we want to draw something that looks like that. Now, there's a lot of ways you might approach this problem. If we were trying to, if this were part of the game, so if we were trying to push line segments as something that we wanted, like a really good-looking end-user, anti-aliased, like beautiful line segment thing, what we would probably do actually is implement some kind of a distance field in a shader, right? Honestly, is what we do. That way, it would be per pixel accurate and all this other stuff, always correct. No math involved outside of it, and off we would go, right? Glyph drawing by using shaders is a kind of a well-known thing right now, and that's something we would investigate if we were trying to draw like really pretty lines for the game. But in this case, we are just in a debug scenario. So really all we need to do is figure out what direction the line is going and construct, we just need to construct these points, right? So what we know is we can compute this vector, right? If this is P0 and this is P1, we can certainly compute P1 minus P0. And furthermore, if we were to normalize that, right, we would get a vector pointing in this direction. With that information, it would then be relatively easy for us to walk out the perpendicular of that and construct something that looks exactly like the diagram that I have drawn here. So if we assume that this is actually from P, I shouldn't say P0, and this is to P, and we want P0, P1, P2, P3 to prepare a proper quad, then you can see that in this case, if we walk backwards along the perpendicular by the thickness, right, this is the thickness value right here, or half the thickness, depending on how we want it, whether thickness is a radius or a diameter. I don't know which we want to consider. It's up to us. But anyway, from P in this case, if we walk backwards along the perpendicular by from P, we would get to P0. If we walk forwards along it, we would get to P3, and the same would be true from 2P. So really all we have to do is produce that little perpendicular. That's our entire job. And we haven't talked much about the cross product here, but that's actually what we would need to use in this case. Technically, we wouldn't necessarily have to use it. There are other ways that we can go about computing this that would involve mapping onto the screen axes first and then doing the dot product. But probably the easiest way is going to be the cross product. So probably the best thing for me to do is just kind of briefly describe what it is and how it works so you can have a little bit more understanding of it. All right. So the cross product is kind of usually talked about in terms of vector products with the dot product. In sort of the old notion of, I think the correct term is vector calculus. I think. But don't blame me if that's the wrong term. In general, there's been a lot of movement away from these ways of looking at vectors, sort of over the course of my lifetime, actually. Not to things that have been invented recently, but actually to things that have been invented a long time ago, but that were just not the predominant way of looking at things. For whatever reason, vector calculus kind of dominated the engineering literature for the better part of the 20th century. I don't pretend to know why. I'm not a math historian. But there are other things. There's, I believe, differential geometry. Is that the... is one of them in computational geometry, or, sorry, geometric algebra. There are these other ways of thinking about vector spaces and stuff like this that have been pushed as more modern or more useful alternatives, even though, again, like a lot of them were actually created quite some time ago. They were not inventions of the 1990s or so, when I think I sort of first saw them being pushed in a wider sense. And you will see a lot of things that sort of talk about the standard vector calc things, which are dot product, cross product, gradient, divergence, and curl. These folks, as kind of being very old school. And new school is like a whole other set of things that I am not even remotely qualified to say whether they're better or worse. I can simply tell you that there is a great deal of discussion about it, and that if this is the sort of thing that you're interested in, you probably would want to take a look at some of these things. Differential geometry specifically is the one that talks about these saucy gentlemen right here, gradient, divergence, and curl. And geometric algebra is the one that talks about these saucy gentlemen. Obviously, there's plenty of overlap in between here. But geometric algebra is basically a way of no longer conceptualizing things just in terms of vector. It's more about sort of like plates and vectors, like vectors and bivectors. And they have, bivectors are sort of two vectors together that define like a parallelogram kind of a thing. And it's sort of a more unified way of looking at a lot of these things. Differential geometry, I know almost nothing about, but you know, for example, there is a book literally called Grad, Div, and Curl Are Dead, and I don't know if it was ever published. The guy, I think the guy who was writing it died before finishing it. He had published an earlier one though that was talking about that, but anyway, it's neither here nor there. So, you know, depending on how much you want to understand sort of all of the powerful ways you could use a lot of this stuff, you may want to look a lot deeper into this stuff than I'm going to mention at all today. But before I mention something like cross product, I just feel obliged to bring this up because while the dot product or inner product is more of a fundamental linear algebra operation that kind of needs to be understood on its own terms, regardless of how you wish to build up the rest of your calculus or geometry understanding. The cross product is not really that way. The cross product is kind of like a special case kind of a thing that's sort of really only useful in 3 dimensions and isn't really probably the right way to think about stuff. Most of the time, if you have a better understanding of these sorts of things, and it's the kind of operator that is specifically why a lot of people would tell you to take different approaches to learning these sorts of things than the traditional method of the vector calculus kind of style, which emphasizes things like dot and cross products as the fundamental way of thinking about things. And so I feel like the dot product kind of survives scrutiny no matter how you wish to conceptualize vector spaces and how they work. But the cross product, I guess I would say, doesn't. The cross product can kind of be thought of more as a special case thing that falls out of these other kinds of ways of doing things, and that probably you should understand those maybe a little bit better if you really want to understand what was going on there. I think that's probably pretty fair to say. I say that as someone who isn't super familiar with all the math, so take it with a grain of salt, but I guess I would just point out that the reason I didn't mention this stuff very much when we were talking about the dot product is I feel like the dot product is kind of universal, and the cross product really isn't. The cross product kind of a hack, and there is a non-hacky way of conceptualizing these things if you wish to kind of dive deeper into it. Or at least there are alternatives. There are proposals of ways that might be less hacky. All right, so all of that sort of front-loading out of the way, let's talk about what the cross product actually is and why you might want to use it, bearing in mind that a deeper theoretical understanding of the math here would lead you to other things, and the cross product would kind of be sort of just this one form of the equations that you end up with if you're only considering a special case. All right. So we know that let's take the inner product or dot product on this side, just so you understand what I'm talking about here. As we said, I write it in its standard vector form. If I have two different vectors here, x, let's say, well, let's not use those. I guess let's use a and b. A transpose b for the dot product. In this case, it's the length of a times the length of b times the cosine of the angles between those two. That we've said many, many times on Handmade Hero. And again, very easy to understand once you kind of get used to it. Construction-wise, you can kind of think of it as if you have, say, for example, a b which is unit length, in this case equals 1, and then you have your a out here. You can think of it as sort of projecting onto this right here. Again, it's that cosine theta term. Here is the theta, and this is sort of that projection onto there forms the cosine theta length of a term. Again, a being the hypotenuse of a right triangle, the right triangle being constructed in such a way. If you think about that fundamental diagram, and I'm saying it quickly because we've said it so many times on Handmade Hero that I hope everyone is very familiar with this. If you're not, I don't know how to say it any more than I have already said it, because we've talked about it so many times. So hopefully you're very familiar. If you're not, please go back to earlier episodes where we talked about the dot product, maybe using that really cool tool by Asaf Gartner to search for inner product or dot product. So hopefully everyone's comfortable with this. What I'd like to introduce today is the cross product. Cross product usually, and again, you can sort of see right off the bat, it doesn't really make any sense. It's written like this. Oftentimes, you can notice not a linear algebra operator here, really. This is a matrix product. I mean, this is a very fundamental kind of product in linear algebra. This is not. This is just kind of like, and it's kind of like a sort of a something that almost a descendant of the determinant of a matrix. It's really, like I said, I just want to emphasize the uncomfortableness of the dot product. Not that it's not very useful to just kind of know how to use one now and then again, but just to keep you sort of with the understanding that there's better math out there that sort of post-dates, or whose acceptance anyway, post-dates when I learned a lot of this stuff, that can help you get more traction on it. Anyway, it's written like this, and it's actually very closely related. It's basically this. It's almost the exact analog. It's basically this, length of A, length of B, sine theta. And so in some ways, it's extremely close to the dot product. But there's one really big difference that makes it not exactly that. And that is that it goes in a direction. So if you take a look at this, in this case, we have a vector here, and we have a vector here. But this contraction of the two vectors together produces a scalar on this side. And so if I wrote the equation exactly like this, that's exactly what we would have for the cross product. We'd have a vector here and a vector here. And we'd have a scalar on the other side, right? A single value. Because remember, the dot product produces a single value, right? And we know how it's produced, right? It's ax bx plus ay by plus az bz, right? So you can see it's a scalar. It's just a sum of a set of terms. There's no vector here. There's only one value. So no matter how long these were, this could have been 9,000 units long, and this could have been 9,000 units long. When we transpose them together, we just get one big long thing of 9,000 terms that all smushes down into one scalar, right? So no matter how big the vectors were to begin with, the dot product always works, and it always produces a scalar, and it always produces the scalar that follows this rule. And again, it is dimension-free in terms of its operation. The only requirement is that the length of the number of elements of A, the dimensionality of A, has to be the same as the dimensionality of B. So I can't dot product a 3-dimensional vector with a 12-dimensional vector, but I can dot product a 12-dimensional vector with a 12-dimensional vector. So as long as their sort of dimensions are equivalent, then I can do this. And why? Because it's a matrix product, right? It's fundamentally something that looks like this, right? It's some number of elements here, some number of rows here, some number of columns here. They both have to be equal, and then I produce a scalar. Okay, so the cross product is not that way. It does not produce a term that looks like this. Rather, this term is actually the length of the result, and the length of the result is actually, the result itself is actually a vector. It's a vector where this is the length, and the direction is some vector, is along some vector c, right, which is perpendicular to A and B. So C perpendicular to A, and C is perpendicular to B, right? So if you imagine the diagram for this, you end up with a thing where this part here, this diagram, this right here is going to be the sine theta times A, for example. If we had B as a unit length again, and we applied the cross product, we would get this same term for the length, sine theta A, right? But rather than just producing that length, we end up with it going in a particular direction. And the direction it goes is perpendicular to both of them. What that means is no matter what these two vectors are, right? So here's the two vectors, let's say, and here's theta, right? We're going to get this as the length, but we're going to get it in a vector that goes in a direction. And that direction is coming out of the plane that contains these two. So whatever this plane is that these two vectors are in, I don't know what that plane is, but whatever the plane is that's formed by these two vectors, right? This result of the cross product comes up and out of the plane. So it's actually another 3-dimensional vector that we're producing. We have one 3-dimensional vector A, one 3-dimensional vector B. We cross them together. We end up with another 3-dimensional vector C, and it, you know, it's time. I guess you could say, depends how I want to do it, but we have some vector. It's going in the perpendicular direction, and it's going to be this long, right? That's what the cross product actually does. And then there's the question of how does the cross product actually do it, right? How do we actually form a cross product that satisfies these things? And you know that we're going to have, right, 3 elements. So we're going to have 1 term, 2 terms, 3 terms. And we know that the length of these things is going to come out to be this, and its direction is going to come out to be this. So we know ahead of time, for example, that whatever this result is, this AB sine theta C, if we were to then cross it with if we were to dot product it with A or B, we would get 0. So regardless of the length, actually, even if we just took just the C term, which is the directional term here, if we said C transpose A, we would get 0. If we said C transpose B, we would get 0. That's just something that we know by the definition of perpendicularity. And so what we could say is that whatever we ended up with here in terms of our values, whatever our x, y, and z were in this case, we would end up knowing that once we dot product them with our original vectors, we would end up with zeros. Now, I don't know, I've never tried to solve for the dot product in that way. I wonder if you just could do that. I know this is probably what no one wants to watch today, but you know, it's unfortunately my show, which means I can do whatever I want. And so I guess I might just ask that question, because I don't think I've ever asked that question. So I know that A cross B equals A, B, sine theta times this C term here. If I know that that has to be the length of it, so what I could say is the length of A cross B equals AB sine theta. And I know that this C term here well, I guess what I could say is I know that A cross B transpose A equals 0, and A cross B transpose B equals 0. If I know all of these things are true, in theory, there are only 3 components to a cross product. Could I just solve, after a long bout with mathematics, for what they had to be? It's intriguing to me and kind of want to see if it's true. So let's suppose that instead of looking at C this way, let's suppose that I just start off by saying that C equals A cross B. That is what C equals. So what I'm really saying here is the length of C, whatever that is A, B sine theta. C transpose A is 0. C transpose B is 0, right? This is what I'm starting with in this case. And so I can write these down, right? I can just say that Cx Ax plus Cy By plus Cz Bz equals 0. I can say that Cx Bx plus Cy By plus Cz Bz. Oops, why did those change? I'm bad at math. Here we go. This is why I could never be a mathematician. All right. So I know that those 2 things are true. And furthermore, I know that this is true. And that's a much more fancy equation, certainly, right? But I could, in theory, if I want to, I think, I feel like I can just square those 2. Right? I don't think there's any particular reason why I couldn't. So I could say, for example, that this term here, I believe, if you just multiply both sides by themselves, since they're equal, that should be legitimate, you'd get CC equals AA, BB, sine theta, right? Which contracts to just, C squared, A squared, B squared, sine squared, I think. I don't see any reason why not. Which is to say that I could rewrite that as just Cx squared plus Cy squared plus Cz squared. Right, that's this term here. equals ax squared plus bx squared plus cx squared. I don't know what I just did there. That's nuts. I meant a y squared plus a z squared. Yeah. Bx squared plus by squared plus bz squared sine squared theta. Right? I mean, again, like, can't say I want to try and solve these equations, but in theory, at least, this is just a known quantity. This is just a known quantity. This is just a known quantity. These are the only unknowns, right? So I've only got, in each case, I've only got 3 unknowns. And I have 3 equations. So in theory, just based on the definition, although the plug-in chugging in this case would be extremely onerous, especially due to this saucy gentleman right here, it sure seems to me like you could do it. And yeah, I don't see a lot of reason why you couldn't. So I would be interested to just shove this into a computer algebra. I don't have any desire to go through and actually try to do that. I would love to be able to solve that in a computer algebra. I'm kicking myself right now for not installing one because actually someone sent me one recently, and I wish I could remember it. There was a freely available one that people had recently been pushing. That I was wondering if we could possibly get to work. I think it was Sage. Was it Sage? Let me take a look here. Yes, this was it. So I wonder if we just, you know, I don't know. It's kind of a saucy Saturday at this point. I wonder if we could just figure out how to use one of these. And you could help me, right? We could learn it together, and then we could have it solve this equation for us because it's not a particularly difficult equation, I don't think. It's just a lot of symbol manipulation in this case. And so I would think that we could get a computer algebra system to do it, I should imagine. Let's see what happens. Here is some download information. I am in America North. The University of Washington in Seattle is actually in my hometown. Is this something that would run on, say, Windows? I don't know. I have no idea what an OVA is. So I guess that's kind of confusing. It says download binaries from Microsoft Windows, so presumably the OVA is what I want. I just don't know what that actually is. I guess I'll just click on it and we'll find out. So yeah. Can't say that's going particularly quickly. And also, if I'm reading this correctly, I guess that's trying to tell me that the computer algebra system is 3.2 gigabytes. Is that possible? Oh God. Well, okay, so that's a little more troubling. Let's cancel that. Wow, okay, so do you have to run it in a virtual machine? Is that really the case? It's a computer algebra system. How is that even possible? I don't know. Let's take a look at some of these other things. Is there anything else we could do here? So that's 57 megabytes. Let's go with that one, shall we? Since we don't really need anything in particular, let's just see if we can get this one to work. Now, bear in mind, the last time I did a lot of serious math work, I used Mathematica. That's the program I'm most familiar with. I have no idea how to use this. Who knows if it'll work or not. Your guess is as good as mine, but I figure we should at least start with one that doesn't require installing a virtual machine to run an equation solver. Your guess is as good as mine. Apparently that's where we're at. That's where we've arrived in terms of our ability to program things these days. Is it requires a virtual machine of 3.6 gigabyte install footprint to run a program that used to be like a megabyte long, and that's just okay. That's where you go. Whew. Okay, I don't know what to make of that. I mean, I'm just trying to put that in perspective. So 1935 right now has a footprint of 120 gigabytes of uncompressed data, and our current shipping footprint for that is 1.6 gigabytes. So the actual thing you need to download is 1.6 gigabytes for a 160 gigabyte footprint game in terms of uncompressed art assets, which of course you'd never really do. But that's how big the actual data pack is. So this thing to run a computer algebra system is twice the size, roughly, of a game that has 160 gigabytes worth of art assets in it. It's impressive, to say the least, I should think. I don't know what they're doing with all of those, but there you go. Okay, so here we go. Let's see if this works here. It's doing its thing, right? You can see it's uncompressing some stuff. Got a little QT going on there. Always good sign. Here's a program. Got a GUI here. See what it does. There you go. Looking good. I mean, that's right. I mean, that's something. Looks like it's got something going on here. I don't know. Let's see what happens. We should probably read a tutorial first, but maybe we can say, in this case, q equals 5. False. Maybe I have to set q equal to 5. Out 5. Okay. So, this shouldn't be too hard. That's pretty understandable what's going on here, I guess, right? This must be equivalence, like does q equal 5? And it's like, no, it doesn't, because you haven't told me what q is. Then I said q was equal to 5, and I just guessed that might be the syntax they use for assignment. I turned out to be right. That was pure conjecture on my part. So then I said, okay, what's q? And it said q is equal to 5. I can work with this, right? This seems reasonable. So let's see here if I can teach it some of these things. I've got some equations here, and so I guess what I need to know is how you do solve, right? And so there should be some way to ask it to solve a system of equations, and that's all we really need to know. So here's some solve. It looks like we've got solve equation variable. That's what we need. The only problem is we need multiple variables, right? And so what we need is a system of equations. So it looks like this is the only one that can solve a system of equations. The fact that they call that old solve doesn't fill me with bristling confidence. But maybe I'm missing something. Let's take a look at what else we got here. So let's see. Here's the definition of it. So it looks like this is all we would really need. So I'll give it a shot. I mean, according to that documentation there, right, I can just put as many equations in here as I want, and I can put in the variables that I'm trying to solve for here, and it should do so. Now, it doesn't sound like it's got a particularly good solver engine, so there's that, but, you know, we'll give it a shot, right? So let's try it. So let's say cx times ax plus cy times ay plus cz times az equals 0. That's equation 1. Equation 2 is just the same thing but with b. And then equation 3 is this god-awful monstrosity here, namely cx times cx plus cy times cy plus cz times cz is equal to ax times ax plus ay times ay plus az times az. That multiplies bx times bx plus by times by plus z times bz. And then finally, we've got sine theta, which I'll just call st, because in this case, we don't need it to know what sine theta is. It's just a term between the, in this case. Oh, well, you know what? I guess that's not true. In this case, sine theta, that is a bit of an issue, because theta is the angle between the two vectors. So actually, I guess that's a tougher thing than I had been anticipating, because in this case, we don't really have a way to specify what that actually means in terms of the variables involved. So that is tougher. I wonder if I can do something simpler first. Because if you think about what this means, right, I have these two things, and in this case, we're talking about this part between them right here is difficult for me to tell it how to construct. This equation is just far too complicated. These two are really easy, right? These two involve nothing but the scalar terms without any real understanding of the relationship between them. But this one is much tougher, and the reason that it's much tougher is because of this term right here. If we could get rid of this term entirely, then we would be in good shape, because then it would still be very clear what was going on. But because this term is there, we have this issue of not really having any way of defining what theta is, because the angle between the two vectors, well, how do you define the angle between the two vectors, right? How do you compute that angle, right? So one way we could do that is by turning to the dot product, right? We could say something like, in this case, we know what the angle of the thing is because we could take the dot product of these two vectors together and use a b cosine theta, which we could compute, right? Since it has both of these terms, the only part that we don't know, again, is that final part. I'm trying to think if there's an interesting way we could go about producing the transform between these two. Because it's got both of these terms in it, so the a and the b stay the same, and then the cosine is the only part that's different. I can't think of any real way of doing that off the top of my head, though. Again, seems pretty complicated. So yeah, I honestly can't say I can think of a good way to do that cleanly. Since we know that these two are the case, right? Since I know that these are the conditions that have to hold true in order to solve for this vector, really what I could say here is that maybe let's ignore this part for now, right? Let's just see if we can get it to solve for something that goes in the correct direction, which is what this is about. This is about the correct direction. This right here is about the correct length, right? So in order to sort of start with, I wonder if we can get something that figures out how to solve for something that goes in the correct direction. And I'd have to think about how I would specify that. So in terms of the length here, I guess what I'll just say is, let's pretend there's some additional, like I said, let's just pretend we know what that value is, and we prescribe it. So I think I'll stick with what I said here. This won't be exactly what we want, but at least it's a start. And we don't really know if this can solve it anyway, right? We don't know if this thing actually has a reasonable enough solver to actually do this equation. But we'll try. It's thinking. Well, I can't say I know what that is supposed to be. Did I input the variables wrong or something? A list of results is returned, and each result is a list containing the values of the variables in var list. Again, at most, a single solution is returned. The task of solving a single equation is simply delegated to such that the equation can be solved recursively. Firstly, because this doesn't make any sense. cy equals cy is hardly a solution because we know that's true all the time. This starts to look a little bit more correct here, but it's still a bit odd. I'm not filled with confidence here. So I don't know about this. I don't know about this, gentlemen. Maybe this is why you need the 3.8 gigabyte version. Well, we tried. Let's at least just say that we tried. Let me see if there's anybody else we should try that's not quite so large. I have no idea what's going on right now. SourceForge, ladies and gentlemen. We're probably getting all kinds of viruses right now delivered to our system. Hello? Okay. So I don't really know. We'll try one more to see, because we should be able to get just some simple solves going here. We weren't even really trying to solve the whole thing there. I was just trying to ask it for a basic preliminary solve that I feel like should have produced something. Maybe I'm wrong about that, but we'll see. I certainly think it would have in Mathematica anyway, using the power of Stephen Wolfram, who personally solves all the equations for you in Mathematica. Let's see here. There we go. Okay. Let's go ahead and get our SourceForge viruses installed. Just some good, excellent virus. Nice, tasty viruses. Viruses within viruses installed on our viruses. Getting some Python in here. For our previous one was in Java, it looked like, or JavaScript, I don't remember. Maybe JavaScript. This one's in Python. So just having some bunch of different languages working on our math here. I don't know if this is actually something that's meant to be end user facing, but we'll see. Give it a shot. Here's a GUI. All right. So let's take a look here. Here's a command. Let's see if we can do the same thing we did before. Argument cannot be an atom or subscripted memoizing function. All right. Well, let's get some help first. Let's see if we can solve, because all we're trying to do is solve an equation here. We don't need differential equation solve. We just need a basic solver. Maybe that's what we need. Let's just see what regular solve does. Solves the algebraic equation, expression for variable x, and returns list solutions equations in x. Expression is not an equation. The equation is assumed in its place. So it looks like this can take a series, right? And so if that's the case, solve the simultaneous linear polynomial equations by calling linsolve or algsolve and returns a list of the solutions. In this case, linsolve. List solution to list arguments. So that's looks like what we would want there. So maybe I can try that. Now the format of the equations, it would be nice if I could get an example of this. So let's just see if just so I get the syntax correct, if that makes sense. So I just wanted to see if I could sort of get an example of solving. See if I can I search inside here? Not really, unfortunately. Back substitute, dimension solve, global solve. Let's see. So here's an example. There's an example of exactly what we need. Global solvers are assigned to solution values from our linsolve. We might need some tweaking here, but we'll try. So here's a solve, right? Let's go ahead and see if it works. So it produced an output where it solved for these guys. So in theory, I should be able to sort of put what we wanted to put in here and see if it works, right? And so let's go ahead and try that. And we'll just give this one a shot. Maybe we'll have better luck this time. So in this case, we want cxax plus cyay plus czaz, right? Here I want cxbx plus cyby plus czbz. That's equal 0. And then finally, got the last equation here, which is the one that's not really correct. That's cx plus cy plus cz, and that equals ax plus bx, plus ay plus az times bx plus by plus bz. And again, I'm just numbing in this term for sine theta, which is not really correct. Right? And I want to solve it for those three variables. I'm going to hit Shift Enter and see if it can do anything here. The answer appears to be no, I guess. That looks like it's telling me that it can't find any solutions. I'm not really sure if that's what it's saying, to be completely honest with you. I wonder if I change this term. What if I just said that the sign between them always had to be 1 or something? Could then it do it? Holy cow. Well, can't say the layout looks particularly good on that one, but at least it sort of did something. Okay, well, that has been our foray into computer algebra systems. I guess what I would say is a little rough. This is kind of the experience I often have with computer algebra systems, which is to say that the notion that they're kind of these things that maybe you could have to just help you out with stuff is a little bit naive. You kind of have to actually take time to learn to use them really well. Like, possibly those ones could have been used to help us here, but it's pretty clear that, like, the idea that you could just enter some math into them and say, hey, could you give us some insight into what's going on here is kind of not true. You kind of just get spammed, and either you get nothing out of them or you get craziness out of them. So that's not really super useful. So maybe I will abandon this for now. I was just kind of curious if we could do that. I was kind of hoping that maybe we could do something along those lines, but it looks like even a simplified version where I'm not even asking it to do sort of the full solve for the cross product is maybe pushing the limit, or maybe I'm just misunderstanding what's happening there. That could also be. We could also try the 3.6 gigabyte one at some point, but I don't want to try that right now because we'd have to wait 30 minutes for it to download. And so, yeah, that's probably not the best use of our time. Anyway, we tried, we failed. That's just how that goes sometimes. Not a lot you can do about that. All right. So I guess what I'll do here is let's just start with the actual textbook definition of the cross product. I'll show it working, and then I will maybe try to think tonight, and maybe people can post what the best way is for us to derive this. I could look up some good derivations of it and just see what the simplest one is. Because there's probably something that's a lot simpler than trying to go this route that we could do to sort of get into it. And maybe that's the easiest thing to do, since sort of the brute force approach I was just curious about took too much time and is not going to pan out. All right, so let's skip that for now. And I will simply show you here what the actual definition of the cross product is. And you can see here there's that diagram that's very much like what we wrote. And you can kind of see here the actual definition of the dot product is actually very simple. This is what I was hoping we'd be able to solve for. And you can see here it looks like they've got a reasonable derivation that's not too bad. I mean, it's a little lengthy in terms of this. It looks like what they're doing is they define a few basis vectors and what the rules for the basis vectors are. And then they can produce the results there. So maybe we could work that one through tomorrow. And show how that works. Here's the part I was talking about, it falling out of the determinant as well. But anyway, so maybe we'll work through that tomorrow, and that can be the way we'll derive it instead, rather than trying to derive it from the properties that we wanted. We can sort of, I guess you could sort of still say that this is deriving it that way, but it's definitely sort of showing a level of understanding of it that you'd probably only have after you already knew what it was. So it's a little less appealing to me than a way where we literally just state what the properties are and then out pops the equation. So I was kind of hoping we could get to it from there. But maybe that's just too complicated and requires too much working it through. I don't know. But anyway, this is the actual standard form of the dot product as you when you actually get through and figure out what it actually is. And you can see here it's, again, 3-element vector. It only really works in 3 dimensions. And you need to go into those other sorts of branches of math that I was talking about to start working on ones that work in more dimensions. And you can see here it's actually got a relatively simple form. It's basically, these 1, 2s, and 3s are x, y, and z, right, in our case. And you can see here that it's yz minus zy, right? So whatever your first, this is a u and a v. It's kind of hard to see here because u and v's look very similar. But if this were an a and a b, let's say, right, it's yz minus zy, right? then it's zx minus xz, and then it's xy minus yx, right? So at the end of the day, even though, like I said, I'm not sure there's a really straightforward derivation for it, even this one is kind of assuming that you already decided you've got these basis vectors and here's the rules for them. So hey, you know, you kind of already have figured out how it works in a sense. Assuming that you actually do work it through, you end up with something that's very, very simple and very easy to code. It just may not be obvious exactly how you get there, right? But at the end of the day, like I said, it's not onerous. It's only onerous to derive in that sense. It's not onerous to actually use. And so if we go to our inner product here, where we've got inner V3, V3, if we want to do a dot product version of one of those, a cross product version of one of those, it's very light on the computation. It's not hard at all. So the result, again, is just going to be equal, in this case, I'll write it out this way. To some very straightforward terms. Is it as simple as the dot product? No, but it's, you know, it's pretty close. So in this case, I'm just going to end up with an AZ BY, and then I'm going to subtract this from an AY BZ, like so. And then I've got an AX BZ minus AZ BX, and then finally I've got an AY BX minus a AX BY. And let me just double check that I've got those terms correct there. Like I said, so it's 2, 3, 1, right? 2, 3, 1. Okay, so no, not quite right. 2, 3, 1. I had these guys backwards. There you go. Go. All right. So yes, we have a YZX, ZXY, and again, these always go in the same order as well. You can kind of see here that it's always XYZ. It's just rolled around, so it's XYZ, 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 right? And again, that's just has them numbered instead of as the actual values. So it's 1, 2, 3, 1, 2, 3. Right, 1, 2, 3, 1, 2, 3. And they just swap from either side. So it's YZ, ZY, ZX, right? And again, it's very similar to the dot product in the sense that the actual reason why you want it is very difficult to understand from the final form, right? And so these equations that I wrote originally are the ones, these are the ones that actually tell you why you care about it, right? Like this stuff right here is actually the important part. But the actual implementation of it doesn't really show any of that. So it's hard when you start, if you just were to look at this, or same with the dot product, if you were just look at this, you'd be like, I don't know why I care about basically squaring the values, you know, or doing x times x, y times y, z times z. I don't know what that gives me. What, you know, why do I care about that? Similarly, you'll care and you're like, I don't understand why this would actually matter. But the reason that it matters is because what it computes is, again, something that's perpendicular to both a and b, both the input vectors, and something which has a length that's proportional to ab sine theta, right? And so any one of these properties may be valuable to you. And in the case, just in the interest of finishing up quickly, in the interest of doing what we want to do here, again, the reason we care is because we want to be able to produce a perpendicular. So if we have this cross product available to us, what we could do in this case is produce a perpendicular that does exactly what we want. Now, if you look at it, you might go, well, how does the cross product help me? What I said is I wanted a perpendicular to this vector, but the cross product requires 2 vectors, and I've only got 1. I've only got the directional vector that goes from the starting point to the ending point, right? How do I end up producing this other one? Well, if you think about it, really, this is a 3-dimensional construction. I've got this line in 3D, and I'm viewing it from somewhere, right? And I want this line to be flat onto the screen. So I actually know another vector, which is the vector coming out of the screen at me. That's the camera z vector. So if I was to cross the camera z vector with, right, that other vector, that 2 vector here, I would get this vector coming up out, right? So the camera z cross the line vector, that is going to give me that perpendicular value that I want, right? Because fundamentally this, right, here's the line, here's the z, this cross this is going to give me something that's perpendicular to both of them, which is exactly the value that I want here, right? Exactly that vector. So the cross product is actually perfect for this. The only problem is its length is not perfect for this. We know that the length will be proportional to the length of these 2 vectors. The line vector, if I just use this whole vector here, is whatever the length of the line is. And the camera z vector is the unit length, so I'm going to get something that's as tall as the line, right? I'm going to get something that would draw a square as tall as the line. But that's okay because I can just normalize that vector down to unit length by dividing by its length, right? I have the ability to normalize a vector. So what I can do is just start with the vector there, normalize it down, and then have the vector that I actually need to be able to draw my line segment, right? So in this case, what I want to do is I want to form that perp, right? So this is going to be basically my, I guess my, I don't know, I could say the vertical or line perp, something like this. In this case, what I want to do is I want to take the cross product, again, of that sort of the line vector itself, which in this case is going to be, you know, the going from the from point to the to point. And I want to cross that with the camera's z, right? So if I go here and I say, you can look at the camera. Now, since this is for debugging, what I would assume we would want to do here is in the render setup, right? What we're doing here, we're storing the transform for both the debug and game. We probably want the debug transform because this is again for debugging, so we probably want to draw those in terms of facing our debug camera, not our game camera, I'm guessing. So what I probably want to do here is say, all right, I've got the cam z vector. The camera z vector is going to be whatever, again, the debug transform is. I'm going to want that z value, right, in this case, like so. And I'll have to also make sure that that debug transform gets set whenever the game transform would get set to. So we might have to take a look at those just to make sure that they're all kosher there. But anyway, so that's what that value should be. And like I said, we want to take that camera z vector and cross it with the line vector. That's going to give our line perp. But of course, we also want to do a normalization on it. And of course, we have that ability to do our normalization on it. You can see here we've got our normalize. Now, again, we want to avoid dividing by 0, and we don't know how long the line is. Maybe someone gave us a degenerate line. So I'm going to go ahead and say normalizer 0 on this cross product so I can get back my perpendicular like so. Okay? From here, it becomes fairly academic. Like I was saying before, we know the construction as long as we have that perpendicular. It's just the thickness times it. So what I can even do here is I can just pre-multiply by the thickness as well, right? So now I know I'm just adding my line perp or subtracting my line perp. So what I want to do is I want to start at the from p, add my line perp, right, for p0. Actually, I subtract the perp, line perp, I guess. I'm going backwards along it, like so. The p1 is just going to be the same exact thing, but it's going to be from the 2p, right? It's going to be out here and coming backwards. Oops. Similarly here, I'm going to add the line perp, and again, add the line perp. And that's really all we need. That's everything we need. And then we can pass everything that we've computed to the push quad to just push the standard quad on, because now we know all of the values that the quad has to take. And that's really it. So now moving on, you can see that we need 4-element vectors, obviously. And that's fine because those are just the only reason we're pushing 4-element vectors on there is specifically because we need that z bias component. In this case, we're never going to bias the z, so we just put a 0 as the final one, and we're good. Our line segment in this case needs to have that line color here. I'm going to just call this C for now because we only have one of them. And I'll go ahead and put that on. You can see if I go back to where our push line segment call was, it needs a from and a to in the C case. So basically we need, let's see here, something like this. And that just allows you to draw a line that would go from one color to another. In this case, we don't ever really need to do that. We're always going to be using just one color for our volume, but you can see how you might want to have that line be different. There we go. I don't know why I left that in there. That was a mistake, obviously. I really need to modify my for-coder config to suck up white space when I do a delete. It wastes so much time that I don't do that, and I just haven't done it yet. I need to do it. All right, so let's take a look here at that push line segment. Oops, push line. And really, we should be in the Q&A now, so I should stop soon. But I think the only thing I need to do is now pass the thickness down. There we go. Oops. Okay. These don't need to be V4s anymore because that expansion gets taken care of a little later, and we don't really want them to be, because again, they need to be cross-producted and so on inside there. So there we go. And now what I'd like to do is just briefly test it before I go to the Q&A and maybe do a little debugging of it just so we can get it working. Inside here, for example, when we're doing this world transform, what I'd like to do is just say, like, okay, let's try drawing a rectangle, just a simple rectangle that we can look at. So if I was going to push a volume outline on here, and I just did, you know, rectangle min-max, for example, and I did 2 of these, or, you know, and just said something that was going to be very simple, like -111 to +111, right? And I'm going to draw that as a purple rectangle in this case. And I don't know what the thickness is going to be. We'll do 0.1f for now. I don't know if that's about even remotely reasonable. That's in world space. It's probably a little too thick. So there's that, but whatever. So let's go ahead and see if I can run that now, and we can just take a look at what that actually does. So I'm going to move back here and take a look. And you can kind of see what we've got here. It's not quite right. It's not awful, but it's not quite right. You can kind of see some rotation there happening. So I think we're not quite doing the right dot product there in all cases. But we're close, right? You know, we're just drawing little like line fins, which is exactly what we had wanted to draw. But we do have a little bit of an issue there. So let's just go take a quick check. Push line segment. Oops, I'm in the wrong function. Push line segment. And let's just take a quick check to make sure that this is sane, what I was doing here. We have the camera Z value and the line Z value. We should double check our cross product. Our normalizing are 0 and our thickness for that seems to make pretty good sense. Here's our 2p and our from p. And so in theory, I would think we should get something relatively stable from that. I'll have to double check just for me, for my own purposes, to make sure that that's really going to give us what we want. But I feel like just think about this for 1 second. Just a hot second. So one of the things with this is, you know, if we've got this in the world, and then I've got something coming directly out of the screen, it is true that the tilt of this vector z-wise is probably going to be dependent on how this is. It's really hard to draw these, unfortunately, but let's say this was the camera z vector, and this was kind of pointing off in that direction versus pointing off in this direction. The tilt of this is going to vary a bit there. So it is also the case that we may want to confine this to only being in the plane of the screen before we do our cross product, for example. So we could do this in a slightly different way that wouldn't involve that wouldn't involve that extra tilt, right? We could do it sort of a way that pre-projects down to the screen. I'd have to think about how that would work exactly, right? But for example, here is the line equation that goes 2p from p. If I wanted to remove, for example, the component of this that is outside of the if I wanted to keep this in a xy plane relative to the screen, I could, if I wanted to, for example, subtract away the portion of it that actually fell in line with the camera's z-axis, right? I could do that. And I should probably explain a little bit more about what's going on there, but hold on one second and let's actually see if this is more what I had in mind. But I don't know that it actually should matter all that much. You can kind of see I'm still getting sort of not exactly what I would have expected there, right? So I want to look at that a little more closely. And the other thing I would like to do is check. I'm going to put that off for now. The other thing I would like to do is check my my cross product, which we haven't actually done, to make sure that the terms in here are correct and that there's nothing weird happening in there. They look right to me at the moment, so I'm pretty comfortable that we have that correct. CXY. Yeah. So that looks correct to me. I'm pretty sure. Get rid of this now. And so my only question is whether or not we need to do anything fancier here. I feel like these should be more stable as we go, especially if you were to remove, like I was saying, if you were to remove the part that is, remove the part of the line that isn't in the plane of the screen, which this should do. I would think that would give you a very stable perpendicular for purposes of the line. But that one looked like it was tilting in a way that was sort of counterintuitive to me, how that would work. So I'm just not sure exactly why that would be the case. I'd have to think about that a little bit more closely here. But again, you can kind of see, how that construction plays out. Again, it's pretty straightforward. So what I could do too here, let me take a look if I remove, just for purposes of inspection, if I only have one of them, so here it is. So you can see the part that's kind of a little bit weird to me, which is that I would expect this to be kind of, there should be a place where it does become singular. When I'm looking directly at it like this, it should be wrong, because of course it can't find, there is no way to like really produce a line in that case, because I'm looking straight down at it. There is no span of the line in the space of the screen. But pretty much everywhere else, I would have expected it to be better in terms of that. So in this case, for example, it's coming out here. And so if you imagine that in the plane of the screen, that is a pretty reasonable perpendicular, I suppose. But it just, I don't know, maybe that is a pretty reasonable perpendicular. I don't know. I guess now that I look at it, it is behaving relatively good in terms of facing at the screen. And it's really only when I look at it quite head on that it becomes sort of tilted like that. So I don't know, maybe that actually is relatively reasonable. And again, all this is trying to do in this case is really just make sure that we're always getting some kind of width towards where the camera is facing, right? We're just trying to produce a 3D width that's oriented towards the camera, which I guess is exactly what it's doing. So I guess I don't maybe have as much complaint as I thought I did originally with it. That actually looks pretty good. So maybe that's fine. The thing I'm not sure about, again, too, is whether we actually care about doing that that step of removing the non-sweep space portion. That might not really be so necessary, but so here that is again. And yeah, I mean, I guess that is pretty good. Now that I look at it, those things are always turning to face me pretty much most of the time. So that's not bad. I'd have to think about whether there's maybe it should be done a little bit better in the case of sort of those ones. Again, they'll kind of spin around when we're looking kind of dead at them because it doesn't create a particularly usable version there. But other than that, yeah, I suppose that's fine. Again, this is only for debug purposes, so I suppose as long as they're always sort of orienting roughly towards me, that's okay. The thickness in this case, like I said, is probably too high. We probably don't really want that kind of thing. Probably want more like this, right? Certainly. And so that's really more what it's supposed to be drawing. And again, when you look at it that way, now it becomes a lot less objectionable, that sort of rotation, because they're not really particularly big. But you can still see the problem, right? When it's head on like that, it just has a really hard time generating that, that value, right? That perpendicular value. So what we could do in that scenario also is we could try to compensate for that, right? We could also try to produce something that's a little bit more aware of that situation. So for example, when we do push the line segment on, what we could do here is say, well, when we produce this line, whatever it's going to be, we could then say, well, let's take the line length, right? And take a look at what it is. So in this case, we take the length squared of the line. Although I guess we're always going to need the length, so we might as well just take the actual length. So we take the length of the line and we know what it is. And then in ordinary circumstances in this case, or I guess now I think about it, we don't even really need to quite do that. What I can do instead is wait till we're done with this, right? I could take the line perp and say, well, okay, take the cross product here of the line perp, figure out what that is, and then let's take whatever the the line perp length is. There we go. And then I'll take the line perp and I'm gonna divide it by whatever that is, right? That's exactly the same thing as we were doing before, and so that will produce the exact same result, right? Or should anyway. Let's go ahead and zoom in there and make sure it does. Oh, and I forgot I still need to do that thickness multiply. Okay, so that will produce the exact same result as before. But now, instead, we have the opportunity, right, to modify this as necessary based on what the length is. So what we could do is say, well, if the line perp length, so if this result that we're getting is just very, very tiny, right? So let's say if the line perp length is like less than the thickness or something, we'll do something else. Otherwise, we'll do what we would normally do or something. And so what we could say is, well, there's some threshold here which, as that cross product degenerates, so as the values come together, and you can understand mathematically sort of what's happening there, right? I've got a sine theta term in here. So I've got my two vectors, and this is the definition of the length of that cross product term. As this sine theta term goes to 0, which it will as these two things collapse, right? As these two things come towards each other, we end up with no vector at all. And so that's not going to be very useful, right? It doesn't matter what the length of the two vectors are that come in. If the angle between them collapses to 0, the sign becomes 0, and then we lose our term. So as this collapses towards 0, what we could do is say, let's substitute something else in there for the perpendicular that we can use, right? And that might help us a little bit. So what we could do is just say, well, whatever, okay, fine. Let's just use, we know the camera's z-axis and the camera's x-axis are perpendicular, so we'll just use that or something, right? The x-axis can be the thing we use for our perpendicular in the case, where we start to degenerate down below the thickness threshold, right? Or whatever, something like that. And maybe that'll help us. So now if we take a look at what happens there, I don't know if we get really much better. It doesn't look like we get particularly better here. I'm going to see what happens if we do something maybe maybe in this case a little bit above that. So I don't know. Let's do something a little more thickness wise. Doesn't look like we're really getting that case happening much at all. Let me just see if this is happening at all here. There we go. So there's what happens if you actually just always substitute in the x-axis, right? And similarly, I could alternatively, use the y-axis, right? And that looks like this. You can kind of see there. And so what I could do here is just say, like, okay, yeah, I want to substitute that in. Why I'm not getting more substitution of that, I'm not sure, because it looks like that's never substituting in. But it should any time the perpendicular length is less than this. But this seems like a very high value, a high bar to set. And it looks like yet it doesn't ever seem to be actually crossing into that territory, which doesn't make a lot of sense to me. Because the length of this this cross product here should get pretty tiny once we get to that case. So I feel like this is an absurdly high value to have to set in order for that to actually be true. Which strikes me as kind of a little bit odd, right? So I feel like there's something bizarre going on there. So maybe I'll save that for next time. We can look at that in a little bit more detail. For now, I'll just leave it going with the way that it was going before, and we can sort of investigate later. So this one will still has the problem of the lines kind of degenerating when they get a little bit too head-on, or when they become a little bit too coincident, right, with the directionality of the line. In this case, I suppose when I look at it too, I suppose part of the problem there so using the camera's z-axis also is not necessarily what we would want for projection, right? So if you think about it, sorry, I'm still not taking questions, but I just want to think it through. So if we take a look at something on the screen, right, and you think about how this is getting projected down, out there in the world I've got something and I'm looking at its projection here. If I want to create something and then I've got, I should say I've got two things, right? One there and one there. And I'm projecting them both onto the screen, and I'm drawing the line between them. If I want to look at a perpendicular to this line in either case, I guess one problem here is that direction itself. Do I actually want to use, for example, the vector to the camera from, the endpoints of the line to determine where those perpendicular values should be? So you do two cross products to produce a separate fin in both cases, because the fin is going to be projected as well. And so what is perpendicular to the camera at either point? It's hard to say, right? Because that line that gets that gets projected into the screen. Yeah, I can't decide on that. Maybe I'll go to the Q&A first, because I feel like this is too big of a topic. I kind of want to go into this in a lot more detail, actually, now that I think about it, because of the geometric construction is a little bit more interesting. So let me go to the Q&A, and we'll deal with this more tomorrow, unless the Q&A is all about it, and then we can keep going. Oh no! Why is the Q&A button not working? Is InsoBot gone? What happened? I hit exclamation point Q&A, but there's no... Does anyone know what happened to InsoBot? Oh, HMDBot handles the Q&A message and seems to be dead. It does seem to be dead. Like, HMDBot's not on there. Like, it's not on the list. So I don't know what happened to HMDBot. HMDBot is dead. That's unfortunate. But, well, all right. You know, that's just what happens sometimes. All right, so apparently, okay, so Desiu says you can solve those equations in Maxima. It looks like somehow your Maxima is actually able to lay out the results properly, which is nice. Ingeniero, what would be the downside of drawing your debug lines as 3D cylinders or extruded rectangles? It seems like that would look a little nice when viewed from all angles. We could do that. Yeah, if you'd like. So a cylinder, in this case, would be relatively simple. The hardest part about the cylinder is going to be the end caps of it, which I suppose we could, maybe avoid to a certain extent. But yeah, a cylinder is not too bad. A cylinder is just, a circle with stuff on either end. If we wanted to do that, let's see. So if we wanted to draw line segments that way, I'll just if0 this part out here. If we wanted to do it as a cylinder, then basically what we're talking about here is just some number of angles around sort of a radius vector, right? And we need to do sort of some of the same things. So we still need to do this. Right, we still need to come up with this, because that's going to be sort of the central direction. You know what, I shouldn't do this in the Q&A, because the same problem is going to occur, just in a slightly different way, which is that we have one axis, and we're going to need to produce two more axes to use as the basis for the cylinder. And we'd have to talk about how to do that. So I think I'd probably rather wait till tomorrow to do that. It's not quite exactly the same, but we still need a way of producing the cylinder bases. And so we're still going to we still have the problem of producing two other coordinates. It's an easier problem because we don't have to care about the camera facingness of it, since it has nothing to do with the camera anymore. But it's still a problem. And someone was saying we should go ahead and do the lines around rooms. And yes, we totally could do that pretty simply, right? Let me see where that happens. Not sure. Those are traversables. Here are volumes. So what I can do here is just say, like, okay, push volume outline. And I don't know, let me just check to see here. I don't think there's anything in particular that has to do with rooms here. I think it's just part of the collision volume. Yeah. So the collision volumes, right, are getting pulled out here. And if I do a push volume outline, I need to just put these on this way. Here's the color. I'll copy the same color we were using for them before. And then the rect min max. What I want to do is just take the volume offset P and the volume dim and just say volume offset P. I think I want rect center dim, volume dim. I think that should give me the rectangle that we want. And I can delete this. So I think that should draw collision volumes around everything. And we should be able to see those in theory here. Now, whether or not that's actually working correctly, I'm not sure. We would have to, because we don't actually, I think, have all the collision volumes set correctly at the moment. I don't really remember. So we'd have to go see. I feel like people have, I don't really remember who has collision volumes and who doesn't. Oh, I suppose the other thing we have to do is actually use the entity transform. So one of the things that we weren't doing in the volume outline case with the object transforms, we're not actually using the object transform here, right? And we would need to. It's got that offset P, and so that actually has to be taken into account here. So I suppose we would need to do something along the lines of this. And I think the scale probably also would need to be taken into account here. So that's you know, the actual collision volumes there, I think, that are involved. And you can kind of see that the head's got one too, that's moving around with the head at the moment, which is again correct, I think, because it's, you know, we're drawing it here, but it actually is correct to where it should be. And so, yeah, you can kind of see where all those are, and those look, you know, pretty good. Those are definitely the tree ones. Look right to me. So I think that's pretty close. Again, I think we want to eliminate that object transform scale bit there. So little by little, we're getting back to something where everything is relatively sane. Now, one of the things that we don't do currently is when we're back in the game view, we don't set the debug view at all, right? And so I'm not sure how we want to handle that. Like you can see here, we got the use debug camera thing. I don't know if we want to do something where we just set the debug camera to be the same thing as the game camera. I mean, one way to do that, and like I said, I don't know to what extent we want to do it this way, but I'm just going to throw it out there as an option, is when we actually do set the camera transform, when we do a push setup, if it's a debug camera, or if it's not a debug camera, we also set the debug camera, right? So we do, render group debug transform equals render group GameXform. So basically, anytime we set the game transform, we also set the debug transform, but you can then override the debug transform. And what that does, right, is that just makes it so that we can, render our debug stuff in the game view as well, so you can actually see them all. So here's the debug camera, right? And then when we switch back, we still get actual placement for some of this stuff. And again, that's just sort of a way for us to make that stuff flow a little bit nicer. Desu said, you mentioned that you use discriminated unions. Have you seen Rust implementation of some types? I have not. I have not really looked at Rust. So I have not seen Rust implementation of anything, really. Jesu23, I was looking at how the vector types are set up in Handmade here as unions. As far as I know, it's undefined behavior to write a value to one type of a union and then read as another type. Is doing something like this well-defined? vecl.x equals 5 and then read as vecl.e0, or is it one of the cases where we rely that a reasonable compiler will do the right thing? The answer there is I have no idea. I pretty much just use C as the best thing I have for an improved assembly language. And so I can guarantee that that works just fine on all the platforms that you ship games on. And so that's pretty much the end of the inquiry for me. As to whether the spec allows it, as far as I'm concerned, the C++ spec is just terrible. Like, I hate it. It doesn't guarantee any of the things that I usually want to guarantee. And so there's tons of cases where there's stuff in there that I'm just like, I don't know how you're supposed to write reasonable code and make use of these features with the way that it works, right? And so I don't know. I have no idea what the latest version of the spec says about that aspect of unions. If you can't do that, then unions are kind of useless, and I don't know why you have them, right? Because if you can't use the values in place, it's really just a space-saving feature at that point, which is very, very limited in terms of its utility, especially nowadays when computers have so much memory. The idea that the only thing you can use a union for is to overlay two types on top of each other in a space-saving way seems incredibly misguided. So I would sure hope that the spec doesn't say that, but it wouldn't surprise me if it did, because the spec says some pretty ridiculous things that I feel like no reasonable programmer could ever really say was a good idea. Would you describe discriminated union to the general public? Sure. So, you know, in programming, even practical programming, not just theoretical programming, a lot of times we're pretty concerned about the idea of defining a collection of named elements that oftentimes, you know, take up space or whatever else. And so a pretty common thing that we would do, you know, in any programming language, in C, C++, there's the notion of struct, right? And we might define one structure, and we say that that structure involves some variables like int x, you know, float y. Wow, that's really good writing there. Right? So in this case, we've got struct foo, int x, float y. It's fairly understandable what we're doing there. Everyone knows what that is. In another case, we may have some other thing here, and maybe that's got something else in it. Maybe that's got like char star name, right? So when you look at these two things, what we've defined here is two separate bags of data. They each have sizes. What are the sizes? Well, in 64-bit world, on an x64 machine, for example, this is 4 bytes. And this is 4 bytes. So this whole structure takes up 8 bytes of space. This guy right here is 8 bytes by himself. He's a pointer, so he's bigger. And so this whole thing takes up 8 bytes as well. These two are the same size. So a single chunk of 8 bytes could be talked about in either way. And really what we're saying is that we've got something of 8 bytes, right? 0, 1, 2, 3, 4, 5, 6, 7. Oops, I could do one more than I needed. 7, right? Really what we're talking about here is this is memory. We can talk about this memory in two different ways, right? One way is the foo way, and the foo way looks like this. This is the foo way, this guy. Here is x, and here is y. Another way is the bar way, right? And the bar way is saying this whole thing is the name pointer, right? It's a pointer called name. In this case, it's an int called x and a float called y. Now, hopefully, we're all very familiar with this idea that basically programming languages give us ways to talk about memory in a structured fashion that lets us quickly refer to some portion of that memory and have the compiler understand the way we want that memory treated, as an int, as a float, as a pointer, whatever, right? So this is just a general thing that basically every programming language has, is the ability to talk about a chunk of memory in a structured way that's more than just what are some bytes that are in that memory, okay? So furthermore, we can usually, in most programming languages, in C, it's called a union. We can talk about something that could be either, right? And the way that we do that is we say, okay, we've got a foo here, and we've got a bar here. And we got some union that's like, you know, foo or bar. And it can be either of these two things. And then what happens in the code, right, and we've seen ourselves use these in Handmade here all the time, is now when someone has one of these, when they're using one of these, they can choose to refer to the foo section or the bar section depending on what they believe the one they have is, right? So a union is just a way of representing exactly what I just drew here. A union is a way of saying, I have a chunk of memory. I might talk about it in one way. I might talk about it in another way. It's up to my code which way it wants to talk about this same piece of memory. And now it's worth noting before I go any further that these two don't have to be the same size. The union will just be defined to be as big as necessary to hold the biggest one. So if this one had a second pointer in there, char star name 2, which would have blown this out to be another 8 bytes long. Even though foo ends here and bar ends here, it wouldn't matter. We could still do this union. It would just be a 16-byte union with 8 bytes of nothing at the end if you were using it as a foo, or all 16 bytes used as if you were using it as a bar. Right? So, structured data, union is a combination of structured data where we say we can look at it in one of two ways, or n ways, we can add more than two. And so then that finally brings us to the concept of a discriminated union. A discriminated union is exactly what its name implies. It is a union, whatever that means in your programming language. In C, it is generally talking about literally a union, like the keyword union. But it may be called something else in other programming languages, right? That includes some way of figuring out which of the which of the elements of the union is actually the one being used in this case. So it looks like exactly like what we had before, right? It looks like that, but now it is wrapped inside a struct and that struct has in it a type field. This is the discriminating part. It's saying that I'm remembering which of the two I was, and I'm writing a code into the memory that is reserved for this to specify which one it is. This is typically an enum. This foo or bar type typically then says, okay, I am type foo, is 1, let's say, or maybe I don't even specify anything. Say type foo, type bar. So this gets assigned to a 0. This gets assigned to a 1. And so then in the code, what I do typically, what the programmer does, not me specifically, is they look at the type field, and that lets them know which of these they're going to be looking at, right? So this is how we get a discriminated union. It's a union of things, but rather than just being a candidate and having no idea which of them might be the one that was actually intended by the person who originally created this memory somewhere early in the program, whoever created the memory is now telling you which one it is, and that's very useful. So typically this gets used with a switch statement. So you say, in this case, I get one of these passed in. Maybe it's I get one of these disk foo or bars, right? So I have a discriminated foo or bar A. I have that here, and then I'm going to say a dot type in my switch, and then I come through and I say case, type foo, and in this case, I use it as a foo, so I'm going to see stuff like a.foo something, right? And then I have a case for type bar as well. Right? And so this is how a discriminated union typically is used. First, there is something that checks the discriminator, right, the thing that tells me what the type of thing is. And then I do different code based on which type it actually is. Hopefully that makes some sense. Now, it's worth noting that, I don't know why. I imagine that somewhere there is some record of Bjarne Strustrup or whatever explaining why he didn't like discriminated unions. I have no idea why. Because rather than properly supporting discriminated unions in C++, he instead chose to use inheritance as the primary model for sort of the poor man's discriminated union. and it took a long time to even get to the point where it could do the things a discriminated union can do. It required RTTI before you could ever even get to that point. RTTI and casting are the only way you can really emulate them. And even at that point, it's really weak and isn't as good as the manual implementation, which is the one I've written here. So for whatever reason, he failed to appreciate the necessity for or underestimated the degree to which category theory demands this, and can clearly tell you that inheritance is not a substitute for discriminated unions, at least not the kind of inheritance that C++ provides. I suspect it was just a lack of understanding of the fundamentals of how programming works, which again is endemic to C++. I mean, one of the things you can say about the design of C++ pretty much across the board is that it lacks any real understanding of the fundamental principles of programming, I would say, either practical or theoretical. Like, I suspect that a theoretical programming perspective person would have no end to the degree to which they thought C++ was awful. And the same thing is true of practical programming. There are just so many ways where you're like, I don't know how you didn't understand how important discriminated unions were, but you didn't. And that's just unfortunate. But you can construct them manually, and that's what I do. In a better programming language, these would be constructed automatically for you. You would just say, I have a discriminated union. The discriminated union is of these types. It would automatically create the type field for you in a stable way that you could control, and blah, blah, blah. But C++ is not that language, and it cannot do that thing. So that's where we're at. Graham 1642, can you give a motivating example for these discriminating unions? Yes, I can. So typically, the point of a discriminated union is really very straightforward, and it happens everywhere in programming. And if I could summarize, I'll sort of explain the importance of discriminated unions by contrasting them with say inheritance, which specifically doesn't support the thing that I'm talking about. So suppose that I have two pieces of code that are separated by control flow in my program. So I have, let's say, to make it very straightforward, I have two pieces of code. I have startup, right? And I have shutdown, let's say, right? And so in startup, what I'm going to do is I'm going to pick whether or not my backend to the code, right, is going to be Vulkan or OpenGL, let's say, right? So I'm going to create a renderer, and I want to create in startup one that's either going to be Vulkan or OpenGL. So I'm going to have some preference, let's say maybe, and I'm going to do an if on that preference. And in one case, I'm going to do like, renderer equals Vulkan. And in the other case, I'm going to do, and I guess like maybe let's do it this way. Renderer equals init Vulkan that returns, one of these things. And in the else clause, I'm going to do renderer equals init OpenGL, right? Because maybe, I've got an OpenGL path, but it's not as good, and I got a Vulkan path that's like more highly optimized because I got, more control off of it or whatever. Who knows what? So some stuff happens here, and I'm trying to figure out which one I'm going to dump to. Or maybe it doesn't even matter. They're both good paths, but the OpenGL one requires some extensions, or I don't know what. Like, who knows? But I've got a preference here. Maybe the user even picks it, which one they want to run. OK? So now in shutdown, I want to call some shutdown. I need to call like dinit Vulkan or dinit OpenGL, right? And so what I want to do here is say, if it was Vulkan, then I want to do like dinit or dinit Vulkan renderer. And here I want to say dinit OpenGL. Right? Very straightforward. Now this is the case where both techniques work equally well. Okay? So if I want to implement this by a discriminated union, you can see how I would do it. The renderer just has a type field in it which says which one it is, and then it has some data that comes after it that is completely specialized to Vulkan or completely specialized to OpenGL, and the person who's using it doesn't have to know anywhere in between here which one it actually is, right? And when it gets to the end, it can switch on the type. Similarly, I could implement this using inheritance by having, I've already said how to do the discriminated union when I just said that, right? But I could do one by inheritance by having, a struct renderer that's some base class here, right? Here's the base class definition. And in the base class, I would have something like init and dinit, right? And these would be virtual calls. Okay? And then I would have a struct Vulkan renderer and a struct OpenGL renderer. And both of these would have a public in them where they inherit from renderer. Okay? Right? We all know how that would look. And what would happen there is in startup and shutdown, instead of doing this, right, you would just have to, in this case, still switch on the preference, and you would create one of these derived classes here, right? But then when you get to shutdown, you never do this if. Instead, what you do is just renderer arrow, right, dinit. And you trust that the virtual function dispatch will call down into one of these two saucy gentlemen here that actually handle the call, right? Hopefully that makes sense. So what C++ decided was this was the only one you ever needed. They were like, I don't understand why you couldn't just implement all your code in terms of this. Look, it works just fine. In here, you just create one of the derived classes, and then at the end, you just call dinit, and you don't do the if, right? Off we go. Everything's fine. However, this is a really shallow understanding of how code actually works, because what it assumes a priori is that you always have what's called single dispatch, which is to say that the only thing that ever determines how a code path will work is the type of one object in the code path, right? Why? Because virtual functions can only dispatch on one type. There is no such thing as a unioned virtual dispatch that dispatches off of the type of two things, right? And furthermore, this gets into a really sort of deep, very core aspect of programming that everybody should understand, and the people who designed C++ should have understand, but didn't, which is that single dispatch is tractable because it is ON, right? Single dispatch is tractable to write as a systemic, sort of stupid derived version here, right? Because it's ON. There's only ever as many dispatches as there are derived types, right? So the n here is how many different derived types we have, and so that's pretty tractable. On the other hand, a double dispatch, or worse yet, triple or quadruple dispatch, or God knows what, right, is n squared, right? Which is completely intractable in most cases, and we can talk about why it's so important to have discriminated unions in order to be able to support n squared, and I can talk about why. So let's say why. So what's double dispatch? Double dispatch occurs in situations, for example, where you've got something like collision detection, right? So let's say I've got something where I want to do, a discriminated union, and I've got, struct collider. Well, the C++ inheritance model would have us believe that everything that you wanted to describe in terms of collisions, right, could be described in terms of like collider, a cylinder, let's say, collider volume, collider, I don't know, cylinder, volume, and sphere, blah, 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 right? So when you have these situations, you've got cylinder, volume, sphere, etc. And each one of these is going to be public collider. You end up in a situation where you're going to have something like, intersects, does intersect, right? And you're going to have to test for intersection with two colliders, collider A and collider B. And right here, already, we're in a huge conundrum as far as C++'s original conceptualization of how types should work. And the reason why you're in a huge conundrum here is because you cannot dispatch at all in a double way, right? There's no way for you to say, I would like to do a double dispatch here where I want to collide two different types with each other, right? And I want you to pick the right one in this matrix that looks like this, right? Cylinder, volume, sphere, cylinder, volume, sphere, like so, right? There's no way to do it. It's literally not a thing that they support originally, right? And the reason for that is because if you just have two colliders, you have no idea. You can't call a function on A and have it know what the type was of B, because you can't know what the type is of B. The whole idea of C++'s inheritance model is you don't know what the type is. They didn't have RTTI at the beginning, so you couldn't even ask what the type was. But you couldn't do sort of a dynamic cast. Later, what they did is they added dynamic cast specifically for these kind of situations where it's like, well, somebody at some point is going to have to figure out what B is, right? Because at that point, we've got a problem. So the poor man's solution to this in C++, and I can't believe they ever thought this was good, but this is what you had to do, was you had to do sort of a round-tripping thing. What you'd do was you'd go down and you'd say, all right, for each of the derived types, I'm now going to write a function on those derived types that calls back into the main type. That calls back into the main type with the properly typed parameter. So what it does is it says, well, okay, the first virtual function call is like begin collide or something. I don't know what I'm going to call this, right? But something, there's a virtual function. When it gets down to one of these types, I have to implement that begin collide in each of these guys, right? And then in each of these guys, I call back into here to a like continue collide call or something, or the actual collide call, with the first parameter of that collide call, or the thing that I'm colliding with, is now fully typed. So I've got collider cylinder in here, collider volume, collider sphere, right? So the first virtual call is the thing that discovers what the type of A is, let's say, right? And then it calls back with its type now determined as the first parameter, and the undetermined type of B is the actual virtual call now, because you call it on B. So first you call A's begin collide, which then calls the collide on B with now the correct type. Okay? So basically the way you implemented double dispatch is you first dispatch on A to get you into the right row, and then you dispatch on B to get you into the right column, and then you finally get to a frickin' function that actually does some collision between two things, right? Now, if that sounds absolutely ridiculous to you, I would say that's because it is. When you want to collide two things, what you want to be able to do is just look at what the type of the two things are, right? What you want to do is you want to be able to write a function that just says collide. And I want to be able to say collider A, collider B, and I want to put all the code in here. This is where the code should go for collision. I don't want it spread throughout the code base in two sets of virtual dispatches that are used to discover the types of things and have to go like jigger all of those to make sure that every single one of them has a call for each different type that it could have ended up with and blah, 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 right? It's awful. I just want to write it in here. And what I want to be able to do in here is I want to be able to compress my ON squared matrix however I want. And this is really, really, really crucial, right? This is the fundamental thing that they didn't get when they were designing C++. I don't know if they were like aware of it and didn't think it was important or just had no idea. I suspect it was the latter, but you know, who knows? The problem here is as these matrices get really large, right? So let's say we have 32 types by 32 types here, right? This would be impossible to implement the C++ way. You'd be typing in so many virtual function signatures all over your code that you would just be crying yourself to sleep every night, even thinking about the disaster that you had created. The point here is no one is going to ever be able to write code that actually involves 32 by 32 different cases handled uniquely, right? It's nuts to think about this, right? That's 2 to the 5th times 2 to the 5th, right? Otherwise known as 2 to the 10th. Forget it, right? You know, no one's going to be writing this many pieces of code uniquely. So what you're always talking about in the case of an ON squared dispatch is you're talking about a sparse matrix, right? You're talking about a sparse set of cases where only certain patches of the matrix actually involve uniqueness and everything else maps into those cases in some way. And discriminated unions are by far the most efficient way to write that code because it lets you think about what you want to think about. You can do any arbitrary Turing-complete analysis you wish to generate the actual cases you care about. So for example, in this case, I can say stuff like if A, if A's type is a cylinder, and B's, and could, and sphere is close, which is some function I'm defining that says whether it's close to being spherical or close enough to be, then I want to do this thing. Otherwise, I want to do something else, right? And this thing may not even be the collision routine. It may just be something that sets some variables here that later are defined to do whatever, right? And so you can write incredibly complicated preamble code working with the types of the different things, solve exactly what you want in terms of figuring out what you're going to do, and then do it, right? And it's very clean, very easy to read. Any programmer can come through now and see how the collider actually works. Take this and imagine it getting dispersed out into tons of virtual dispatches on all sorts of different objects strewn throughout the code base, often in multiple files. And you can quickly see why this is just an untenable way to try and write a complex sparse matrix contraction using the tools that C++ gives you. Discriminated unions are very, very good at representing complex interactions between varying types. And they're able to do that in more ways than one. This is one of them. The other way is the memory way, right? That they happen to all also be the same size because they overlay on top of each other, which also allows you a lot more freedom with how you work with them in other ways. So that's also a plus, but that's a separate plus that has to do with memory layout that's not really related to the bonus of the discriminated unions. And so the takeaway here, if you believe nothing else about what I said, hopefully at least it's put the thought in your head that being able to write code, complex code, which looks at the way in which types are set between among more than one object, is crucial to well-functioning code. And that is where discriminated unions really shine. C++ is sort of Procrustean, I guess I might call it, amateur conceptualization of how types should have been discussed. At its foundation, is really just way too primitive and forces you to use something much, much weaker than a full Turing-complete language in order to, well, I shouldn't say full Turing-complete, one that makes it almost impossible to access the Turing completeness of the language. You could probably eventually, if you wanted to, construct everything you needed out of virtual functions, right? But it's just not a good way to write it. So what I should say is it robs you of all of the expressive power of your language and forces you to create the compression of your dispatch matrix in terms of an incredibly convoluted set of calls that can only use one thing, which is a virtual dispatch. Why would you want that, right? There's literally no reason for it. It doesn't give you anything in return. And that's the really cruel part of it, is that if you go down that road of thinking, you're doing an incredible amount of work, you're not getting anything back. The discriminated unions give you everything that you could have wanted, you're giving that up, you're not getting anything in return, right? And so that is the really, really crucial part of it, is just that ability to talk about the types using plain language with the power of functional decomposition and equivalences and being able to look at the state of more than one thing at once. Being able to write that code very cleanly is the real power of discriminated unions, and I cannot stress enough how much more powerful that is than inheritance, which is very, very weak by comparison. Now, like I said, unfortunately C++, because at its outset it believed in this inheritance model, which is, in my opinion, just complete, it's just complete amateur hour. It's bad. It's a bad type system. It's just not very good. You don't get the benefit of having the language help you with your discriminated union construction, which I think is one of the reasons why people don't like it as much in C++ or think that inheritance is good, is because the language doesn't really give you any real support for discriminated unions beyond just the union keyword, which was already in C. But again, other languages that have a more a deeper understanding of what types are and why they're important don't make that mistake. And in those languages, discriminated unions should shine even brighter. They already, even though C++ did not appreciate them and has never supported them properly, they're still actually one of the best ways to do types in C and C++, despite the fact that the designers of the language never understood them. And I think that's also a testament to just how powerful they really are. But you can imagine how great it would be if your language actually supported them. So people in the chat have been suggesting that Rust is a language that does support them properly. I could not say. I have not programmed in Rust. But again, I would encourage you to look to other languages where people designed them who had a better understanding of why types are important and how they work, because those languages always do support discriminated unions, and they are going to support them a lot better than C++, which has never really embraced them. All right, I gotta wrap it up soon. We're way past the point where I was gonna be done talking. Cubercaleb says, how would you feel if you wrote the functions for colliding each pair of types and allowed the compiler to generate the sparse matrix of function calls for you? The answer is that is what this is, right? That is what this is. This collide function with a switch statement is exactly what I want, right? And the reason for that is I don't want to just write a few sparse cases here. The whole matrix needs to be full a lot of the time. It's just that I don't want to actually have different pieces of code execute everywhere. I oftentimes want subtly different ones that just set some variables different or whatever, and that is what this gives me, right? A collide function which reasons about the types, sets up some state, and then has a switch statement that does a few different cases depending on which one I'm doing, is exactly what I want, right? If that makes sense. So yeah, and again, that's just. I would highly recommend it also if you think that it's a matter of opinion, whether discriminated unions are good or not. I would highly, highly suggest that you sort of maybe look into category theory, because my understanding is actually that discriminated unions aren't a practical question. You can actually theoretically prove that they are required to do computation the way that you want to do it, if this makes sense. Like discriminated unions are like a fundamental concept in terms of how to do efficient computing. So I am not equipped to make those kinds of arguments. So I certainly would not be the one to make that argument at all, as opposed to convincingly. But my understanding about discriminated unions is actually, it's not just like oh yeah, my sort of opinion is they're practically useful. It's like, no, they're like theoretically required to properly think about programming. You actually need them. They are a fundamental part of the math. And so, I guess what I'd say is ignore them at your peril. Because I don't think it's really a case of like, this guy says they're good, this other person says that they're not. It's a lot more fundamental than that, if that makes sense. Close some of this stuff down here. Let's see here. This is not going to give me very much information, I assume. So this is mainly the computer science part of it. I wish we had maybe pseudonym73 on here to give you a good reference for this, because I don't really know where it is, and this is kind of a really bare bones sort of a bare bones one. But really, like, you need to get a little deeper into this to be able to give any kind of really sort of deep understanding of why they're important. But like I said, I feel like this goes into the math. It's not just a matter of opinion. I guess I would say, like, if you want to know a little bit more about that aspect of it, hopefully there's some way we could get some references on it. Unfortunately, a lot of these things that are sort of about the sort of fundamental truths that they are sort of start to discover about programming are not always made available to practical, practitioners such as myself or the other folks in the chat. A lot of times, the literature is just extremely impenetrable, and it's like, unless you really devote a great deal of time to it, it's very hard to really understand what's being said. And so, unfortunately, you end up in this scenario where, like, learning about how essential some of these things are can be incredibly difficult to really suss out. So I'm just going by what people who know category theory have told me, and like I said, it's something that I've never had the I guess time to really sit down and decide to pursue. So I cannot give you even remotely a way to think about that end of it. All I can tell you is that practical programming wise is extremely important. I can guarantee you that. But that's very different from saying that that it's theoretically important, because that involves a lot of things that are way out of my area of expertise. And Sinocron says, "Are you hoping JAI will have discriminated unions?" Certainly, I am, but I'm not very up to date on JAI at the moment. It may already have them, So, all right, I'm going to wind down here. Thanks everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with a source code so you can play around with it yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page you can go to if you want to support the video series, a schedule bot you can look at to find out when we're going to be live, and an episode guide that lets you know sort of what's happened in the past and allows you to catch up on old material. That's about it for today. I'll be back here tomorrow at the same time. I'll be doing a later stream again tomorrow, 2 p.m. Here in Pacific Daylight Time. Until then, have fun programming, and I will see everyone on the internet. Take it easy, everybody.